Welcome to our newest chemistry video on the topic of acids and bases. Today we will be discussing early theories about acids and bases, the first of which belonging to the famous French chemist Lavoisier! Yeah! I was wondering how long I could keep that up. But first, so we've got Lavoisier in 1777. He proposed that oxygen was the universal acid. In fact, he was so confident in the fact that oxygen was the universal acid that he literally named oxygen acid former. That's what it means, in case you didn't know. It means acid former. Unfortunately, he was wrong, because not all acids contained oxygen. In fact, when hydrochloric acid was proven to be made of just hydrogen and chlorine, well, then his theory was entirely just kicked to the curb. They're like, you're wrong, Lavoisier. So then, in 1887, we had this Swedish chemist guy, Arrhenius, and he decided he wanted to come up with a universal theory in light of this new knowledge. And he said that an acid is a compound that dissociates into a hydrogen plus ion. So basically just a proton. When it dissociates, when it dissolves in solution. And bases, on the other hand, would dissociate into hydroxide ions, or OH minus. And that was his theory, and it's a pretty good theory. It's surprisingly close to the actual theory we have today, which is called the Bronsted-Lowry theory. Why is it called that? Well, because two chemists in 1923, Martin Lowry in Cambridge and Johannes Bronsted in Copenhagen, both came up with the same idea at the same time and published it at the same time. It's really got to be annoying. I mean, it's just like, you thought it was going to be the Bronsted theory, but no, that idiot Lowry over in England came up with it too, so they have to share the name. But anyway, the Bronsted-Lowry theory is pretty simple. It focuses on the transfer of the proton, or H plus ions, solely in a reaction. For example, the reaction between hydrochloric acid and ammonia, well, HCl and NH3. They combine to form NH4 plus, or the ammonium ion, and Cl minus, or the chloride ion. And so that gives you a pretty basic definition of what a Bronsted-Lowry acid and base is. The acid in this situation is hydrochloric acid. It gives the proton over to the base, which is ammonia, NH3, because it accepts that proton, the H plus ion, to become ammonia. Well, ammonium. Yeah. And so basically, our simple definition of acids and bases for Bronsted-Lowry is that the Bronsted-Lowry acid is a proton donor, and the Bronsted-Lowry base is a proton acceptor. And this creates a unique situation when it comes to reactions, because once your reactants in an acid-base reaction become your products, they have now switched. The products of ammonium and chloride, well, now ammonium, which used to be ammonia, the base, is now ammonium, the acid. And chloride, which used to be hydrochloric acid, the acid, is now chloride, the base. And that gives us the idea of conjugate pairs that Bronsted and Lowry came up with. And it's basically that for every acid that goes into a reaction, you have a base conjugate pair, which is just going to be called a conjugate base. So another example, water combining with just a hydrogen plus ion, a proton. So H2O plus H plus yields the hydronium ion, H3O plus. Well, water before had been the base it was going to accept. But now on the other side of the equation, H-hydronium is a acid. It can give that extra hydrogen ion, that extra proton, in another reaction. So it makes it very easy using this to simply predict how equations will go in an acid-base reaction once you know that everything has a conjugate pair. So, for example, if you want to know the conjugate base for hydronium, H3O+, well, you just remove a proton, H2O. That's your conjugate base. How about NH3, which would be NH3. So that's going to be ammonia, right? And you want to know the conjugate base for ammonia. Well, then you're going to have to assume that on its side of the equation, it's an acid. And what is our definition of an acid? Well, it's proton donor. So we'd give it up, and it would form NH2 minus. I don't really know what the name for that is. And if you go H2CO3, it gives up 1, and you get HCO3. It's a pretty simple idea. So, moving on. The only exception here is that some species can act as acids and bases. Yes, it is not a mutually exclusive group. People from the acid club can join the base club and the other way around. It's really weird. There's a lot of intermingling. And these compounds are known as amphiprotic. Why amphiprotic, you ask? Well, divided into two parts. Amphi and protic. Protic for proton, amphi for both. So it can give both ways. It does it both ways. And thusly, let's have an example. Let's take our first example. CH3COOH plus H2O yields CH3COO minus plus H3O plus. In this situation, it's pretty easy to see that CH3COOH is our acid and H2O is our base. And on the other side, we've got a conjugate base and a conjugate acid based on your originals, right? Switched around. However, let's have another example. NH3 plus H2O yields NH4 plus OH minus. Well, in this case, NH3 is the base and H2O is the acid. But in the last equation, H2O was the base. Whoa! Well, the answer here is pretty simple. It's just sometimes a compound has more than one proton to give and can also accept protons. It can do it both ways. It's just a pretty simple feature. Like if something has two protons, as in the case of water, well, I can give them up, but it can also accept another to form an ion. And that's pretty much it. Amphiprotic has to, if you want a technical definition, it must possess both a lone pair of electrons and a hydrogen that can be released as an H plus ion. And that's your really technical definition there. But other than that, that is it. That is all for our simple theories of acids and bases. We'll be moving on in our next videos to the properties of acids and bases. We gotta describe those things. See ya.